Well, this is a fun lecture. We're starting to get into spatial statistics, and so we got to cover some fundamental principles before we can start getting into quantifying spatial continuity, spatial estimation, spatial simulation, and so forth. We got to build some basics, and so this lecture will be fun. We'll get into those basics that we need to cover, and so let's get into it with some comments. First comment is that this is all going to build on past lectures. I had a student, it was actually really interesting. They asked me last year, they're like, well, how does this all connect up? And it does. Everything we're doing still relies on probability theory. We're still using univariate and bivariate statistics. Sampling, the bootstrap, all of these things still matter to us as we continue to proceed. Okay, so it's all building up. So let's provide a concise and practical definition of the random variable. We'll get into random functions, and then we'll spend some time looking at pretty pictures of brick walls. It'll be kind of fun. Okay, the random variable. So if we do not know the true or actual value at a location or time, and it can take, therefore it takes a range of possible values that can be fully described by a PDF or conversely by the CDF, that's a random variable. So I'll give you an example. A random variable, we will represent it with a capital letter variable, so X capital, at location U bold is the location vector, index 1, so our first location, can take on any one of these possible values between 5 millimeters to 20 millimeters of grain size. And it is completely defined by its PDF, which is shown here. So this is a random variable. At a location in space, we don't know the actual value. We might have some information that helps us constrain what it might be. And so we provide a distribution of possible outcomes at that location, and that is describing that location as a random variable. So that's a random variable. So far so good, right? Just we don't know, it's uncertain, it can take on multiple possible outcomes. Okay. What's a random function? A random function is really not that bad. It's a set of random variables correlated over space and or time. We're still going to represent it as a uppercase, but now it is a suite of random variables at distinct locations. We could sample from that random function or those individual random variables. And when we do, that's a realization, and I'll talk about that right away, but that'll be expressed as a lower caps or small caps variable. And so in general, our spatial context, we could describe data or realizations, X at U1 through UN, our number of locations that we have data or that we have realizations, and they could, or if they are realizations, they could be sampled from a random function described at these locations. So let's visualize that. Random variable at location U1. Random variable at location U2. Random variable at location U3. And if they're all jointly correlated with each other, that would be considered to be a random function. This is very fundamental because the use of random functions and random variables is exactly how we accomplish so much within geostatistical modeling of the subsurface. It's all built on these random variables, random functions. What is a realization? An outcome from a random variable or a joint set of outcomes accounting for correlation from a random function would be considered to be a realization. Once again, it's represented as lowercase variable, so little x. In the spatial context, we'll continue to use the idea of U with an index to indicate a spatial vector at multiple locations, 1 through n locations that we're concerned with. So any type of resulting simulation from a Monte Carlo simulation to a sequential Gaussian simulation, which is really a set of Monte Carlo simulations, any type of method that samples jointly from a random function or individually from a random variable, this is creating realizations. We will in general consider our realizations to be equal probable, but that is not necessary. We could of course have distinct scenarios, which we say some are more likely than others. All kinds of things can happen when we put our uncertainty workflows together. We'll talk much more about uncertainty later on. So if we have a random variable and it has its associated PDF indicated here, if we draw a single value just using Monte Carlo simulation, we already talked about Monte Carlo simulation, that drawn value of Monte Carlo simulation we call a realization. Now, if we have a random function, and so I've tried to represent this, probably not, it's not a great looking figure, I'm sorry, but we have multiple locations, u, 1 through 4, and I indicate it with a box and whisker drawing the concept of a PDF at each single location, 1 through 4. It's getting narrower as we go from 1 to 4, suggesting that perhaps we have maybe some type of data constraint or something going on over here. And it's causing less uncertainty as we get closer to the data, more as we get away from the data. Okay, so a realization from the random function would be jointly sampling from all 4 of these random variables such that we're accounting for correlation. You notice how I've indicated here that we sampled high here for location 1, high here for location 2, maybe a little bit more medium for location 3 and 4 right in the middle. They're not willy-nilly just kind of jumping up and down. I'm trying to show that there's a degree of correlation going on here. Realization number 2, Monte Carlo simulation from the random variable. We got another value, that's realization number 2. Realization number 2 from the random function, we've got 4 more values that are jointly sampled, accounting for correlation between each of them from the random function. Kind of cool, eh? I could do this all day. I could keep drawing realizations, and we would do that as many are needed in order to perform our calculation, our analysis. We'll talk about that later. Concepts of random variables, random functions, and realizations from a random variable or random function have been described so far. Okay, let's talk about stationarity. What is this stationarity thing? So the problem is this. In order to do any type of modeling, prediction, and so forth, we need statistics. In order to calculate any single statistic, you need replicates, multiple samples that we can work with. And so in many of our problems, air, water, beer, anything that we're monitoring a line, we can turn a tap and we can extract a sample. We can come back later that day, turn the tap, extract the sample, and we can do replicates over time. Many of our problems, we have that opportunity to do that, and we can formulate our statistics. We can talk about predictions and inferences. Everything needs statistics to do that. In our geospatial problems, things are different. We don't have repeated samples or replicates available to us in space. If you were to drill a hole in the earth and to extract a core sample that looks like this from that location in the earth, if you go back to that location later that year, or the next day, or a decade later, what will be there? The answer, a hole in the ground. You've extracted the sample, no other sample is available for you. You do not have replicates in the spatial context. So what does this mean? It means that we have to make a decision. If we don't make that decision, we're stuck. So instead of time, turn in the tap, get some beer, check the clarity, the color, whatever they measure on beer or on oil or gas or water, and then come back and do it over and over again. Instead, we must pool samples over space to calculate our statistics. This decision to pool samples over space is what's known as the decision of stationarity. It is a decision, I don't want to get too technical here on all y'all, it's a decision that all of that stuff that you pooled together and sampled is the same stuff. That we can treat it as the same and we can extract statistics from it. Yeah, very interesting, right? Okay, so let's get into more details about stationarity. What can you do if you do not make a decision of stationarity? If you say, no, that's way too much, we don't want to make those types of choices, we can't know that. I'm just going to sample at all of these locations within an area of interest, but I'm not making any decision of stationarity. If you do that, what do you have? You have a table of samples at specific locations, and you know nothing about what's going on in between. You know nothing about the general relationships between them. You are effectively stuck in the hole, in the wellbore, in the drill hole, whatever it is, you're stuck at those locations. You know nothing about what's going on between. You can't calculate any statistics. You can't make any predictions about the behavior of the subsurface between the samples, away from the samples, and so forth. You are very much stuck. So we can't get away from it. We're going to have to make a decision of stationarity, but don't worry, it'll be fine. So let's talk about some multiple components to try to clarify furthermore on this decision of stationarity. First, we have what I would deem as an import license. That's our decision of what data to pool together in order to evaluate the statistic of interest. Take our example here, 1, 2, 3, 4 through 7 data. We pool them all together and we get a distribution that we can now use in order to support everything we're doing with decision making and modeling. That choice of exactly what data we could pull together, that 1 through 7, was the import license. That's the decision of what data to put into the statistic. We're saying they all come from the same stuff. They can be pooled together. We could decide that 1 is different than the rest, and we could go ahead and remove it and work with 2 through 7. We could add 8, 9, 10, 11, 12, and so forth. This is a pretty important decision. The export license is the choice of where we can use that statistic. Because once we have that statistic of the property of interest, the metric or the statistic that we're worried about, where can we use it for the purpose of prediction and modeling? I draw a dashed line. Maybe we say that we can use the statistics gathered from these data within this dashed area. Perhaps it has to be smaller. Perhaps things are pretty homogeneous and well behaved and we can go even further away. That is the export license. That's the component of stationarity about where we can use the statistic. Well, so let's give a couple of formal definitions for stationarity. This one, even though I'm an engineer, I do have a strong interest in geology. I have quite a bit of experience and so forth with the geologic context and the data sorts and so forth, so I will go ahead and write something like this. The geologic definition of stationarity is that the rock over the stationary domain is sourced, comes from the same provenance, deposited, the sedimentary depositional type of processes are very much the same, preserved, the post-depositional diagenetic type of alterations are very similar, and that this domain, this part of the surface that I consider to be similar, is mappable and may be used for local prediction or as information for analogous locations within the subsurface. Therefore, it's useful to pool information over this expertly mapped volume of the subsurface. I think that's a very careful definition of stationarity, paying attention to the geologic context. And so I show an outcrop figure here. You can see different units, perhaps are deep water complexes, complex sets, or so forth, and they have distinct different types of rock properties and so forth, and maybe we identify these as being stationary domains based on what we're trying to measure and what's the problem we're trying to attack. credit to Andre Fildani, a good friend of mine over with Equinor, and his other co-authors for this work. I believe it's out of the Chile outcrops, beautiful outcrops. Toured around with them before to look at those. Thank you, Andrea. Now, if we were engineers about it, we would use a more statistical, mathematical definition of stationarity. But I hope you can see that there's not a disconnect between the two. They are mutually supportive. And so stationarity would be the metric, the measure, the statistic of interest is invariant under translation over this domain, this space. So you could consider a variety of different statistics, and we could write them out mathematically based on the concept of stationarity. The expectation of the variable of interest, z, it's a random variable, at various different locations, would be equal to m, a constant. It does not change. It is, the mean is invariant under translation for all locations that we're interested in. The distribution, f of u being the location vector, z being the property of interest, is only a function of z. The location is not important over the locations we look at. The CDF, F capital, is the same everywhere for the variable z. The semi-variogram could also be considered stationary. That is, the semi-variogram of the property z is only a function of the lag vector h, and we will talk about semi-variograms pretty quickly here, and has nothing to do with the location over the locations we're interested in. So, for stationarity, the mathematical definition will always contain two parts. What's the metric, or I should say the statistic, and what's the volume or the region over which we are considering. We could extend this to any statistic of interest, including facies, proportions, bivariate distributions, multiple point statistics, my favorite, the 13th percentile, or kurtosis, whatever statistic we're interested in, transition probabilities and so forth, could all be deemed stationarity. In fact, in the spatial context, we must make that determination in order to calculate those metrics. Stationarity is a decision, it is not a hypothesis. Why do we differentiate that? If it was a hypothesis, we would have a statistical test for it. We do not have a statistical test. The best we can do is we can work with the data with geologic context, expertise, all put together, and we can demonstrate if our assumption, or decision I should say, of stationarity is appropriate or not. In addition, stationarity depends on scale. This is a figure from the book that Clayton Deutsch and I worked on and was published back in 2014 on geostatistical reservoir modeling. And in this figure, what you can see is that we have some type of spatial phenomenon, just a one-dimensional spatial phenomenon, and we have clearly non-stationarities going on, and so we map those non-stationarities or transitions over space with a dashed line. If you zoom in, what you find is that your evaluation of what was non-stationary or what was variant over space would refine. You'd start seeing more and more details. And so in general, part of the stationarity decision has to do with what is the scale that you're looking at. What scale are you evaluating these spatial phenomena? So let's go ahead and take an example, and we can look at this concept of scale and its impact on the decision of stationarity. So anyone out there who is from the UT Jackson School of Geoscience should immediately recognize this as the wall across from your building when you're sitting out front, having a nice relaxing time sitting in those tables. Look across to this wall in the building beside you across the way, and you will see it. And it is a really interesting wall. It has a lot of different features. And so let's think about this. Is this wall stationary? Just sitting back, looking at the entire wall all at once, is this wall stationary? This is the part where you think about it a bit. Okay. Now, Many of my students today, or a couple days ago, thought that this wall was stationary. And then I asked the question, what was the metric? What were you looking at? And it was cool. A lot of students were pointing out that there was these VOGs, which I thought was pretty cool. The engineers knew to say VOGs. It might have been the geoscientist or two in my class, but there's VOGs. And some students were looking at the colors of the bricks, the size of the bricks, the aspect ratio of the bricks, or whatever it might have been. And they looked at the image and they thought, well, it doesn't seem like there's more or less. It just seems kind of more homogeneously heterogeneous. And so they all agreed, after some discussion, that it was stationary. Well, zoom in. So let's zoom in right here. What about this? Is this stationary right here? And this is the part that was interesting. A lot of my students said, well, no, it's more VOGs over here, less VOGs here. These bricks are lighter, long aspect ratios. These bricks are kind of lower aspect ratios and darker colors. And so they start to say, no, this seems like it's kind of a non-stationary type of image. I said, okay, let's zoom in again. You zoom in on that one brick. Is that stationary? And now everybody recognized that, wow, if you ignore the mortar right there and just look at the brick, that's a very, very stationary image. And then I said one more zoom in. And everybody agreed that this is highly non-stationary. Big VOGs here, kind of smaller VOGs here, a big old inclusion of some sort, some class here within the rock. And so what everyone realized was that as we go through 4 different scales looking at this rock across from the Jackson School, we found, or this brick I should say, across from the Jackson School, you can see that there we go from stationary to non-stationary, to stationary again, to non-stationary again. So it really seems that the scale is very important. Okay, there's many people who hear this discussion about stationarity and they're concerned. And you should be a bit concerned, because this is clearly the heart, the kernel of the subjective component of modeling the subsurface. And so people might be disturbed by that or uncomfortable with it. And so here's some words that will not reassure you. Specifically, you cannot avoid the decision of stationarity. You really only have a couple of choices. Extreme cases, you could say no stationarity decision. Then you can't move beyond the data. You can't populate, well, you can't pool any data to calculate any statistics. You can't do anything to make predictions. Conversely, you could assume, just say, well, okay, it's just all stationary. I'm not going to be too committed. I'll just say everything is stationary. That's a very, very strong assumption. If you start to say that all data over large volumes of the Earth is stationary, that's a very naive way to look at the Earth. And you'll find that the result will be uncertainty models, which we'll get into uncertainty modeling soon, which will be so broad and not very useful for the purpose of making decision making. So you got to walk that line. You've got to do something in the middle. You can't hide your head in the sand. You've got to do something. Once again, geomodeling stationarity is a decision over what region you're going to collect data together, your import license, what region you will then use the resulting statistics from your data, that's your export license. Now, don't be fearful, because the world doesn't have to be stationary. We can find non-stationarities or things that are variant over space, and like the dashed line in that one-dimensional example, we can map that, we can model that, we can use secondary information from seismic, we can use all kinds of things to help us. We can map it, put that into our model, and then work with a stationary residual with our statistical and stochastic, as we will talk later, stochastic approaches. You could also treat those trend models as somewhat uncertain, have multiple scenarios. So we are not hemmed in. We have a lot of options for dealing with non-stationarity. The point is we have to understand stationarity and we have to work with it, work with its framework, use it to be able to collect statistics to build statistical models of the subsurface. I always like to give this caveat right now. Good geological mapping and data integration is essential. I'm never suggesting that this is a purely statistical problem. And the decisions of stationarity will form the framework of any subsurface model. So this is critical to everything we've done. Here's a definition once again of stationarity, kind of a nice, concise one. To the students in my class, this would be the type of thing I would ask about for sure. And of course, with everything else I've just talked about. The statistic metric is invariant under translation over an interval. Now, I made a bunch of comments about replacing space for time because we don't have multiple samples over time, but I don't want to narrow us down. You could, in fact, work with stationarity and a stationary assumption for a problem that is just one location in space over time, in which you have samples over a time interval, and you're deciding where you can pull those samples if the system changes over time. So of course you could have stationarity considerations over just a time system. I just used the common application of replacing time with space to help demonstrate and explain the concepts. Whenever we make a decision of stationarity, we got to decide what is stationary. You need a metric. You need to work with statistics at this point. And so we got to know what statistics we're concerned with. Over what interval, we need a time or a volume of interest. With those two, you have a complete definition of your stationarity decision. It'll always depend on your model purposes. If you're trying to model a phenomenon for which you only have to understand at a very large scale, you may not need to work with very fine scales. You may make grosser assumptions about stationarity. It always depends on the resolution of your data and over what scale you're trying to work. The decision is not a hypothesis, therefore it cannot be tested. It can be, in fact, shown to be inappropriate given available data and geologic knowledge, and it can, of course, be supported by geologic knowledge and by available data. Here's a summary slide where we provide a bunch of the information that was talked about as far as stationarity. And in addition to that, if you follow me on Twitter, you'll see that I like to put out summaries, these infograms that have a whole bunch of summary information about an important concept from geostatistics, statistics, machine learning, and so forth. And so this is one on stationarity. It's also available on GitHub. I've started to put lecture material and so forth up there. So I hope that that's useful to those of you who are trying to use the concept of stationarity within your own classes, within your own lectures, and so forth. I hope that this was helpful to you. To be honest, this course is going to get so much more interesting from now on because we are into spatial statistics. We'll be transitioning into machine learning and talking about uncertainty analysis. And those concepts to me are really, really fun to work with. All right. I hope this was useful. I welcome any comments or any ideas for improvement and so forth. Thank you.